All right, welcome back everyone to week 10's week 10's discussion session. So let's recapitulate ourselves to what we saw in the previous week. So in the previous week, we started with a new mode of heat transfer, which was radiation heat transfer. We looked into the basic introduction to radiation heat transfer, and then subsequently looked into the various fluxes that are involved in radiation. And then we ended by looking into a very important aspect, which is known as the radiation intensity and emission. And as you can see from your screen, we defined something which is known as the spectral intensity of emitted radiation. And we looked into the most generic definition of it. And then, we saw that uh, if we want to consider the total emission taking place in all possible direction, we define something which is known as the hemispherical emission. And then we looked into uh, expression which define the net emission in terms of the spectral intensity of emission in all possible direction, which is nothing but the hemispherical, which is nothing but the hemispherical emission or the total emission. Okay. And then we looked into the special case of a diffuse body where we say that the intensity of radiation is independent of which direction we are looking at. And and then we basically say that the intensity of radiation then becomes a function of just the wavelength. And thereafter, incorporating that, we got a very nice expression which relates the intensity of radiation to the emissive power, which is nothing but the spectral emissive power denoted by E lambda, as you can see from your screen. And the ratio of E lambda to I lambda, which is the ratio of the spectral emissive power to the spectral intensity of radiation, is pi for a diffuse body. That pi factor actually came when if you can see this integration from your screen. Uh, so if you can basically see this integration just reduces to pi, and that's the reason why you got this factor pi over here. And if you want to draw some clarity why this integration actually resulted in the integral of a cos sine and this function is because if you pay a little bit attention to the hemisphere that we draw, you can see that any elemental area that we draw on this hemisphere denoted by a unit normal n, which is nothing but the unit vector in the radial direction er, you can show that. So basically what you can do is you can show that the elemental area dan simply turn out to be r square sine theta d theta d phi. So you can so this form of this elemental area is nothing but the elemental area one gets when you choose an unit normal in the in the r direction and take a differential area on the surface of a sphere or a hemisphere. This is something you get. Okay, so our very definition of solid angle, which was d omega n, and this just turned out to be dan by r square. And if you just substitute this form of r square over here, you get the solid angle subtended by that small patch that we are kind of looking at. So this is nothing but the small patch, which is dan, and the solid angle that is subtended by this small patch basically come out to be equal to, so this r square and r square would get cancelled, and this just comes out to be equal to sine theta d theta d phi. So in principle, this sine theta d theta d phi is nothing but the solid angle that is subtended by the differential patch that you considered on the surface of a hemisphere on, this differential area dA1. Okay, and the cos theta factor is that comes because we are looking into an area which is normal to basically dA1, and that's the reason why in this integral you get a sine theta d theta d phi, which is a solid angle, and this dA1 is just the normal direction basically. Okay, so I hope this is clear, and this is where we looked into in last class. And then we saw the special case of a diffuse body where we said that the intensity of radiation is independent of direction, and then we integrate this over the surface of the hemisphere to get this uh, factor pi. Okay, and then we said that we can now define a total emissivity, which is nothing but either you integrate this spectral emissive power in along all the possible wavelength, and if you do that, you will get a relationship between the emissive power of a black body, which is nothing but the total emissive power, and IB is nothing but the total intensity of radiation. Okay, so just by integrating, so this relation, since we derived it as a spectral property, if you want to get the total property, it's obvious, you just need to integrate it in all possible wavelength, choosing a differential wavelength d lambda. Okay, and that's all what we did it in the last class. Now, for better understanding, what we will do today in this week is that we will start off by solving a problem involving this emission or this intensity of radiation. And once we are done with solving that problem, we'll then move into the emissions from real surfaces, because so far we have been defining something which is known as the black body. We have not defined real surfaces, or in general, we have not quantified something which is known as emissivity. So we'll see emission from real surfaces. So basically, before that, we will also look into or touch upon a topic which is known as band emission, and then go into defining the properties of real surfaces. First of all, we'll look into emissivity. Subsequently, after that, we'll look into something which is known as spectral emissivity and things like that. Okay. And thereafter, if we have time, we'll look into the Kirchhoff's law and special surface, which is known as gray bodies. Okay. All right. So this is the agenda for this week. So we'll start off, as I said, by solving a problem involving this intensity of radiation, because I believe solving this problem would make you clear about how to actually utilize the intensity of the expression of the intensity of radiation or the emissive power that we derived in the last class, or what we discussed just before this. Okay. So I would like you to read the question, which is just on your screen. And if you can see, it says that you need to consider a small area. The small meaning that the area is differential, is of differential nature, whose magnitude is 10 to the power minus 4 meter square, which emits diffusively. So it says that this particular patch of area, it emits diffusively with a total hemispherical emissive power of E1. So so what this question is asking you, or what this question is stating, that you have a small patch of area denoted by dA1, as you can see from your screen. Okay, this is emitting diffusively, or you can say that this is a diffuse body. And recall that the meaning of diffuse body is the fact that your radiation properties are independent of direction. This is something that you can infer. And and that being said, it says that it emit diffusively with a total hemispherical emissive power of E1 equal to 5 into 10 to the power 4 watt per meter square. Okay, and this is what this is what the physical picture actually look like. This is what the area A1 look, and it basically emits diffusively in all possible directions. Okay. Now, given this scenario, what they have said is that at what rate is this emission intercepted by a small surface A2, which is oriented as shown. So given that A1 emits diffusively in all possible directions, what the question wants us to find or to evaluate is that at what rate the emission that goes out of dA1 or A1, which is small, is intercepted by another small surface A2 of magnitude 5 into 10 to the power minus 4 meter square, oriented in this manner. Okay, and this is the first thing that we need to find. And the second thing that they asked us is to evaluate the irradiation G2 on A2, basically. So after finding the emission that is intercepted by A2, we need to also find the irradiation that falls on G2, on this area A2. Okay, that falls on basically the area A2 is what the question wants us to evaluate. Okay, so there is something which is known as so we'll not touch upon that topic today, but in the next class we'll look into the topic which I just now said is something. So there is something which is known as the radiation view factors, and this question is something related to actually building the fundamentals of radiation view factors. Although we'll not utilize the name view factor, but essentially this is how the view factor is defined, or how the very definition of view factor come into the picture. But anyways, we'll not formally introduce view factor today, but as I said, this concept of solving problems something like this actually builds up into something which is known as radiation view factor, and which the details of which we will look it in the next, in the next week. Anyways, so so first of all, as I said, what we need to evaluate is the first quantity, which is the rate at which the emission that goes out of 1 is intercepted by this area 2, and we'll denote this emission as Q12. And the second thing is basically the G2, that is the irradiation that falls on the differential area A2. Okay, so we'll start this so we'll start the solution by drawing motivation from the definition of intensity of radiation, because we define that the intensity of radiation that is emitted from, a body 1 as a function of lambda, okay, is equal to the radiant energy that falls on so it's the radiant energy that leaves body 1 and that will strike body 2 at a particular wavelength lambda, divided by, if you can remember, the normal area in that particular direction, which is dA1 times cos theta 1 times, the solid angle d omega. Okay, but here is the thing that you need to understand. Since I am interested in calculating the emission that goes from 1 and is intercepted by 2, I need to now consider the solid angle that is intercepted by 2 on 1, and this is something that that you need to pay close attention here. Okay, so this d omega 2 from 2 to 1 denotes the solid angle. Oops. So it denotes the solid angle intercepted by A2 on A1. Okay, and then how do we calculate this solid angle? So basically this d omega 2 on 1 is nothing but, so from the definition of solid angle, it just becomes A2 cos theta 2 divided by r square, where r square is nothing but, so this is basically what r square looks like, or it's better to write r2 square, because we are denoting this particular distance as r2. Okay, so this is what r2 looks like, and this is how we define the solid angle that is intercepted by 2 on 1. Okay, I hope this form of the solid angles definition is clear. So this is obvious, right? Because see, this is A2. If you want to find the solid angle that is intercepted by 2, okay, on 1, you need to consider the normal, which is A2 times cos theta 2, and then you need to divide it by the distance, which is r square. Okay, and that's what we have exactly written d omega 2 from going from 2 to 1 in terms of this quantity. So what we require to find, if you remember, we are required to find this quantity q1 to 2 lambda. Okay, so if I now rearrange this expression, I can write q1 2 as a function of lambda. This becomes the intensity of radiation emitted by 1 for a particular wavelength lambda times dA1, okay, cos theta 1, and d omega 2 1, I can write this, so how can I write this? So this d omega 2 1, this can be written as A2 cos, in fact this would be dA2, because these are differential areas, which means that these are very small. So this is dA2 cos theta 2 by r2 squared. Okay, all right, but there is a catch here. So it says that you need to understand that this intensity of radiation emitted by 1 as a function of lambda, this essentially is a function of theta, phi, and of course it is also a function of lambda as well. Okay, but because the question says that 1 emits diffusively, so the question says that 1 emits diffusely, I can then say that IE1 lambda, which in general is a function of the direction theta and phi and lambda, but now since this is a diffuse body, I can just say that this is just IE1 of lambda and it is just a function of lambda. Okay, and then I can utilize the relation that we have derived, is that if I have a diffuse body, so for a diffuse body, I know that my emissive power of body 1, which is, of course, you can say that this is a function of wavelength, this is equal to pi times the intensity of radiation of 1, which is emitted, and of course this is a function of wavelength. Okay, so I can then write that my intensity of emitted radiation is equal to the emissive power divided by pi. Now, the reason why we are doing this, because in the question, the intensity of radiation is not given, rather the emissive power is, the hemispherical emissive power is basically given to you. Okay, so this relation we can utilize first of all because it's a diffuse body, and in the question the reason why we are doing this is because in the question they have given us the hemispherical emissive power. Okay, which means I can now substitute, this form. I can now substitute this form into this expression, and then I can, calculate this q12, which is the emission rate which is leaving one and is intercepted by 2, is equal to, this is E1 lambda by pi. Okay, and then this areas dA1 cos theta 1, and then this is what, this is dA2 cos theta 2 by R2 squared. That's it. I have all the magnitudes here. So for instance, my E1 lambda, this is the hemispherical emissive power. This is given as 5 into 10 to the power 4 watt per meter squared. Okay, dA1, that is the elemental area A1, this is given as 10 to the power minus 4 meter squared. Theta 1 is given as 60 degrees. Okay, theta 2 is given as 30 degrees. dA2 is given as 5 into 10 to the power minus 4, and this R2, this is given as 0.5 meters. So that's it. Everything is given. You just need to substitute the values to calculate this emission rate. Okay. And if you just substitute, I have already done this calculation. You'll get this emission rate as 1.378 into 10 to the power minus 3 watt. That's it. So physically, what it implies is that considering one as a diffuse body, the amount of emission that is intercepted by body 2 is this much, is what actually this q12 of lambda essentially quantifies. Okay, all right. Okay, that's the first part, and I hope you understood the calculation and the physical aspects and the essential what to say, nuances of this question. In the second part, what they have asked you to evaluate is the irradiation G2 on A2, and that is rather simple, because if you know the rate at which energy is intercepted by 2 that comes from 1, the irradiation, as I said, so this is something that we have discussed extensively in the last class, the irradiation, which again is a flux, this will simply be equal to the fraction, or it's not fraction, the emission that comes from 1 that falls on 2, which is q12, divided by the elemental area A2. Okay, that's your irradiation, and of course, since this is a flux, this will have an unit of watt per meter square, and this is rather simple to calculate, right? Because see, what is irradiation? It is the radiant energy that is emitting by some source, okay, that is falling on the desired surface where we are essentially trying to calculate the irradiation. So now the source is 1, it is emitting some radiation, and the radiation that is intercepted by 2 is basically equal to this much. So the irradiation is nothing but this intercepted radiation divided by the area of the object 2, where we are essentially trying to calculate the irradiation, is basically what the quantity irradiation signifies, and that's the reason why it is just q12 of lambda divided by 2. Okay, so if you calculate this, just simple, so this is 1.378 into 10 to the power minus 3 by the area, which is 5 into 10 to the power minus 4. Okay, and if you do this, you will get the irradiation to be equal to 2.76 watt per meter squared. Okay, that's the irradiation on 2 is what we are asked to calculate. Okay, all right. Although it's just a problem where you need to substitute values, but the build-up of this problem is important, and you need to understand the fact that so when can you basically write this thing that your emissive power is equal to pi times the intensity of radiation, and all those things are essential. Okay, although the problem looks simple, but these concepts are essential in understanding the key aspects of intensity of radiation and emissive power. Okay. All right. I hope you understood this, and with this, I believe you have understood the basic concept of irradiation, emissive power, and all these things. Okay. So moving on is something that I wish to discuss today is the next topic, and as you can see from the screen, it is known as band emission and emissivity. Okay. So actually, before introducing this band emission, you must now at least try to realize that when we learn the other mode of heat transfer, for instance, like conduction, we actually never care about the directional aspects and as well as the wavelength. Of course, the wavelength doesn't come into the picture in case of conduction because the mode of heat transfer is entirely different. But at least we are also not interested in the direction in which we are looking at. We just say that if, let's say, if you're considering 1D heat transfer, it's just that the heat transfer is taking place in one dimensional. But in radiation heat transfer, things are seemingly different, and in fact they are actually different. Okay, so first of all, you need to understand that the basic difference that we saw in radiation heat transfer that was not present in conduction or in fact in convection is that your emissions which we calculate here is essentially a function of wavelength, that is at which wavelength we are essentially trying to quantify the emission, and also it's a function of direction, and that is from where if you want to calculate the total, if you want to calculate the emissions in all possible direction, we define something which is known as the hemispherical quantity, basically, which, for instance, the hemispherical emissive power or the hemispherical intensity of radiation. Okay, so that's the directional aspect that comes into the picture. The second thing is the wavelength aspect, which is that at each and every wavelength there is emission, basically. So the emissions that we see is essentially a function of wavelength. So if someone asks me that what is the emission, basically that comes from, that is in between a certain band of wavelength, then we need to define the emission in that particular band only, and that is from where the name, actually the band emission, come into the picture, solely because of the fact that the emissions that we represent are also a function of what wavelengths we are essentially looking at. Okay, so in order to give you a picture, if I now plot something, let's say, so what can I plot? Let's say I'm plotting the spectral emissive power of a black body, okay, as a function of wavelength. Okay, so in principle, the spectral emissive power, and let's say I'm considering the wavelength from some 0 to a particular value of lambda. So when wavelength is 0, maybe I can say that this emissive power is somewhere here, and then as a function of wavelength, this spectral emissive power basically varies something like this. So let's say I'm looking into looking into a particular wavelength, let's say lambda 1, and then I ask you that what is the spectral emissive power at this particular wavelength lambda 1, then this just then let's say this is some E lambda 1 of B. This is the emissive power that I basically desire. Let's say I'm looking at some different wavelength, let's say some lambda 2. Okay, and then if you ask me the emissive power, this is the emissive power that it would be. So you can now appreciate at least that the spectral emissive power, let's say, you can also consider the intensity of radiation as well, that's the same thing, but what I want to emphasize is that these properties are indeed a function of wavelength. Okay, now if you ask me that how much is the emission that is taking place in between the wavelength 0 to lambda 1. Okay, so like the question that I seek to understand is that I seek to know the radiation emission in the range 0 to lambda 1, that is in this range, how much is the emission that is taking place. Okay, so from the knowledge of integration, I can then say that if I just integrate from 0 to lambda 1, this EB lambda d lambda, this should give me in principle the emission between 0 to lambda 1. Okay. If you then ask me, okay, I now want to know the emission which is in between, let's say this band, let's say from lambda 1 to lambda 2. Then the emission from, lambda 1 to lambda 2 would then simply be integral from lambda 1 to lambda 2 EB lambda d lambda. So this is nothing but the emission between lambda 1 and lambda 2. Okay. In that context, okay, I hope you have understood this. I mean, to this end, I hope you have understood these aspects at least. Okay, so what I now want to say that in that context, okay, there is something which is known as a band emission function. And by the way, these intervals from 0 to lambda 1 or lambda 1 to lambda 2, these are known as bands of wavelength, and that's the reason why this name band emission function comes. So the band emission function is defined as follows. Okay, so this is known as the band emission function, and this is denoted as f, let's say from 0 to some particular wavelength, let's say lambda I, and this is just, so this f0 to some generic wavelength lambda I is defined as integral 0 to lambda I EB lambda, okay, d lambda, and actually this band emission function is a fraction, so this why the total, so the denominator we have to consider it for all the possible wavelength, and that's why this becomes integral 0 to infinity EB lambda d lambda. Okay, so physically what, so then I hope you can now interpret physically what this band emission function represents. It says that out of all the possible emissions taking place from wavelength 0 to infinity, what is the fraction that lies in the band 0 to lambda I? For instance, when I becomes equal to 1, the band emission functions basically gives you the fraction of, emissive power that lie within the band 0 to lambda 1 out of the total emissive power, which you get when you integrate the spectral emissive power from 0 to infinity as a function of wavelength, of course. Okay, so for instance, as I said, let's say for the interval 0 to, let's say, lambda 1, my band emission function would then be defined as f0 to lambda 1, and this is nothing but, if I integrate the spectral emissive power from 0 to lambda 1 EB lambda 1, which is of course a function of lambda, and this is d lambda divided by integral, that is the total emissive power in for all the possible wavelength, which is integral 0 to infinity EB lambda as a function of lambda times d lambda. But this quantity, that is the integral of the spectral emissive power of a black body over all possible wavelength, this is nicely given by the Stephen-Boltzmann law as sigma times t raised to the power 4, which means that I can now write the band emission function for 0 to lambda 1 as integral 0 to lambda 1, the EB lambda, the spectral emissive power, d lambda by sigma times of t raised to the power 4. That's it. That is exactly, the fraction of emission, or this is the fraction of the emissive power which is lying in the band 0 to lambda 1 out of the total emissive power which is lying in the band from 0 to infinity, okay, which is nothing but sigma t raised to the power 4 for a black body, and that comes from the Stephen-Boltzmann law. Okay. I hope you have understood this. Now, if I now ask you that what is this quantity f lambda 1 to lambda 2, okay, that is, if I now ask you that what is the fraction of, the total emission that lies between the wavelength lambda 1 to lambda 2, which is actually this. So then from the definition of this band emission function again, okay, I can write that this is actually integral lambda 1 to lambda 2 EB lambda d lambda by sigma times of t raised to the power 4. And then this integral, by using the fact that integral a to c, or let's say I can write that, let's say integral from b to c, some function of f of x dx, this can be written as integral from a to c f of x dx minus integral from a to b, okay, f of x dx, where this a is less than b is less than c. Okay, so in this domain you can basically write this integral that the integral from b to c is equal to the integral from a to c minus, you just need to subtract this integral. So if you use this concept of integration, then you can write this as integral from 0 to lambda. The reason why we are writing this will be very clear shortly. So this integration can be written as integral from 0 to lambda eb lambda d lambda minus integral 0 to lambda 1 eb lambda d lambda by sigma times of t raised to the power 4, and this is nothing but f lambda 1 to lambda 2. And again I repeat, this is the fraction of emission, or this is the fraction of the emissive power that lies within the band lambda 1 to lambda 2. Okay, I hope this is also clear. We're just utilizing the basic properties of integration. All right. So the reason why we are writing this form as this form is because of the fact that, so you can now actually see that if you just consider the definition of, let's say, f0 to lambda. So what is f0 to lambda? It is nothing but let's say this is lambda 1, so it is nothing but integral, as we saw, it is integral 0 to lambda 1 eb lambda d lambda by sigma t raised to the power 4. So what we'll do is we'll multiply the denominator and numerator by the temperature T, and then this becomes integral 0 to lambda 1 times T eb lambda, okay, d of lambda T by sigma times T raised to the power 5, which means you can see that f0 to lambda can now be represented as a function of lambda times T. Okay, and that's the reason why we want to represent this. So the idea is, once you define your wavelength, define your wavelength, let's say lambda 1, you kind of know the fraction that lies between 0 to lambda 1, and that's the reason why we want to establish or want to write everything from 0 to that particular quantity in terms of this. And the reason why we know is because you can define an inherent function which relates this band emission function or fraction in terms of this lambda t, and this relation so basically it's an empirical relation, and this is established. So you can see I have written it from the screen that for a particular multiplication of lambda times t, you have a particular value of, say, you have basically the value of this band emission function. And I have taken this table from the book of Incropera, and you can see, for instance, if you have lambda 1, let's say some wavelength, and the temperature, you can basically evaluate this lambda times t, and then there is a direct relation, because you know that this band emission function is a function of lambda times t, the relation that we just now saw. Of course, this is an empirical relation, but this is well tabulated in the literature, which means that if you know lambda t, you basically know the band emission function. Okay, and that's the reason why and this band emission function is known from actually 0 to lambda, and that's the reason why we establish everything from 0 to a lambda I, rather than writing from lambda I to lambda j, basically. Okay, so that's the idea why we have written this form as basically so why we have written this form as a term, as a function of these two integrals. And now I hope you can then see that so if you now see, you can then write this f lambda 1 to lambda 2 as just integral 0 to lambda 2, okay, eb lambda d lambda by sigma t raised to the power 4 minus integral 0 to lambda 1 EB lambda T lambda by sigma T raised to the power 4, which is nothing but F 0 to lambda 2 minus F 0 to lambda 1. So this is a very important property that if you want to find the band between any lambda I and lambda j, you just need to calculate for, let's say, j is greater than I, okay? And for that, what you need to do is you just need to calculate F 0 to lambda j minus F 0 to lambda I. And this is a very important property that we can extract from these band emission functions. Okay. Again, the reason why we are defining this from 0 to lambda I, because you can establish that this f0 to lambda is essentially a function of lambda times t. Okay, so if you know lambda times t, if you know the wavelength, if you know the temperature, you can essentially calculate what is f0 to lambda. And this is so you cannot actually derive the analytical relation, but empirically this is known, and this is what it basically turns out to be. Okay. All right, so I hope this is clear up to this. If there are any doubts, like please do let me know. Okay, so I believe the band emission function is now clear. The intensity of radiation is clear. The what to say? I mean, the emissive power and all those things are also clear. But if you realize what we have been doing so far is that we have been considering surfaces to be black. For instance, we saw that the emissive power of a black body is basically equal to sigma times T raised to the power 4, and this can also be written as integral over all the possible wavelength, the spectral emissive power, which is a function of wavelength times d lambda. So all these things that we saw, this is true for a black body basically, okay? But in general, things may not be black. For instance, I mean, in reality, we encounter real surfaces. And in order to quantify that, the black body is essentially taken as a reference, is basically taken as a reference body. And then there is something that people define, which is known as emissivity. And this is something that we have already saw in the week's lecture series. So emissivity is denoted as epsilon. This is actually a function of temperature, and it is defined as, this is very important, so this is defined as the total emissive power, okay, of a real body to the total emissive power of a black body. And if you are considering these total quantities, this epsilon t is essentially known as the total hemispherical emissivity, or sometimes it is also called the total emissivity or the total emissivity. So sometimes the hemispherical word is omitted, and if you are, you need to understand that if you are said something which is let's say you are, so if someone tells you it's a total emissivity, you must also understand equivalently that it means it's the total hemispherical emissivity. Okay, and this is defined as the total emissive power or the total hemispherical emissive power divided by, you know, the total emissive power of a black body. And we know that from the Stephen-Boltzmann law is that the total emissive power of a black body is just sigma times of the temperature of the black body raised to the power 4. Okay, and that's how the total emissivity is defined. So you can understand that the total hemispherical emissivity, or equivalently the total emissivity, is equal to the total emissive power of the real surface divided by the emissive power of the black body, which means you know that this emissivity is essentially a fraction which basically lies between 0 and 1. Okay, this is the next obvious thing that you can interpret. Now, in the same spirit, I can write I can write this quantity that we have now defined as the total emissivity of a real body. Okay, or okay. So first of all, one more thing you can infer is that you can now write the total hemispherical emissive power, or the total emissive power of a real body, is equal to the emissivity times sigma times temp t, TB raised to the power 4, and this is basically, the, so this is nothing but, the total emissive power of a real surface. Okay. All right. So I hope you are with me so far. So now what you can do is you can also define something which is known as the spectral emissivity from the very definition of total emissivity. So what we saw is that the total emissivity is defined as ET, which is the total emissive power of a real surface to the emissive power of a black body, and then I can write this ratio as integral 0 to hold on. Yeah, so I can write this ratio as integral 0 to infinity, okay, the spectral emissive power of the real surface, which of course it now becomes a function of wavelength times d lambda by integral 0 to infinity, okay, EB lambda, of course it is now a function of lambda and temperature. Okay, so this is obvious, right? Because the total quantity, I can write it as a spectral quantity integrated over all possible wavelength, that is from 0 to infinity. So this is basically equivalent to this. I hope you can realize this. Okay, so then since this fraction is represented something like this, I can now define equivalently a spectral emissivity denoted by epsilon lambda, and this can now be written as E lambda, that is the total spectral emissive power of the real surface, which is now a function of lambda n t, to the spectral emissive power of a black body, which is of course a function of lambda n t, and this epsilon lambda is known as the spectral emissive power. Okay, so this epsilon lambda, this is known as the spectral emissivity, because we have written this in terms of this fraction. Okay, so while the total emissivity is defined as the total emissive power of the real surface, or the total hemispherical emissive power of the real surface to the emissive power of a black body, which is, so basically epsilon was E of t by EB of t. You can equivalently define a spectral emissivity which is equal to the spectral emissive power of a real surface to the spectral emissive power of a black body. Okay. So, and equivalently, this epsilon lambda, this is known as spectral emissivity, or you can also write this as a spectral hemispherical emissivity. Okay, that means while the former was not a function of wavelength, as you can see, the later, which is the spectral emissivity, is a function of wavelength. Okay, because now we are particularly looking at one wavelength of interest. And that's the reason why it basically becomes a spectral quantity, as we saw. Because whenever you say it's a spectral quantity, it's a function of wavelength. Okay? And in the same spirit, one can also define something which is known as the spectral directional emissivity. And this is defined as epsilon lambda comma theta, because now this becomes a function of lambda, it becomes a function of direction as well, and of course it's a function of temperature. So this spectral directional emissivity is the ratio of the spectral intensity of emitted radiation for the real body, which is a function of lambda, theta, phi, and temperature, to the spectral intensity of radiation of a black body, which is also of course a function of these quantities. So now the spectral directional emissivity is defined as this epsilon lambda theta, and you can see that now this is a function of wavelength, and also it's a function of direction as well. So you can now understand the hierarchy, right? So we define the total emissivity, which is not a function of direction and wavelength, it is just the total quantity. Then we have subsequently reduced this, and we have came to a particular wavelength which we define it as the spectral emissivity. where we saw that it's not a function of direction, but that's a function of wavelength. And then we saw the spectral direction emissivity, which is a function of wavelength, and it's a function of, the direction that we are looking at, for instance this theta comma phi, and this is defined as the spectral intensity of radiation of a real surface to the spectral intensity of radiation of a black body. Okay, and of course this is known as the spectral directional emissivity. Okay, so I hope this is clear up to this point. Okay, so I'll stop here for a couple of minutes. If you I'll ask you to basically go through whatever we have saw, and then after that we'll solve a nice little numerical on this. Uh, I mean, using this quantities that we have just now defined. Okay. In the meantime, what you can do is you can so if you are done with just going through whatever we have learned, there is the numerical that you can see from your screen. I'll ask you to read this numerical on your own, and eventually I'll explain this and I'll show you how to basically proceed from this. And I'll just come in 2 minutes by filling my mug with some water. I'll just come in 1 or 2 minutes. Okay. Welcome back, guys. Sorry for the interruption. So, as I said, we will now be solving actually a very realistic problem, I should say. Uh, and then we'll understand these quantities like the spectral quantities and all, and this band. So in through this example, we'll also understand how to apply the band emission fraction or function that we just now defined some couple of minutes back. And as you can see from your screen, it says that a diffuse surface, first of all, it's a diffuse surface. So readily you can interpret that the emissions are not a function of directions. But it says that the diffuse surface at temperature 1600 Kelvin has the spectral hemispherical emissivity shown as follows. So now you can interpret that the emissivity of this surface, of course, it's a real surface. You can interpret because its emissivity is not equal to 1. It says that the spectral hemispherical emissivity, which we define it as epsilon lambda, this has the following variations. Okay, from this band of wavelength 0 to some let's say from 0 to let's say up to infinity, you can consider here. Okay, and given this, it says that so what you need to do is you need to define the total hemispherical emissivity and the emissive power. Okay, so so that's the question that they're asking. Now, first of all, you need to understand that although your surface is diffuse, the emission is a function of wavelength. Okay, that's the first thing, because of course the emissivity you can see is not constant at all wavelength. For instance, in between the wavelength band from 0 to 2, your emissivity is 0.4, and between the wavelength 0 to 5, your emissivity is equal to 0.8. Okay, so the first and foremost thing that you need to understand is that in reality does this happen like this. Because if I ask you that what is your emissivity at wavelength 2, then you would say that it's kind of a step function, right? Because you can equivalently say that at 2 your emissivity is 0.4, and someone can also argue that your emissivity is 0.8 at 2. Okay, so in reality this is actually not represented as a step function, because if you capture the variation of this spectral emissivity as a function of wavelength, the real graph would look something like this. So actually the real graph would be something like not like this. So the real graph would be kind of like this. So that's what the real graph would look like. So if you have a device which can measure the emissions across this wavelength, this is the blue curve is something that you should get. But for the sake of analytical treatment, what we are doing is we are mimicking the behavior of this blue curve as this step function rate in this exercise. So what we are doing is we are saying that this is equivalently represented by this step function. So this is the real curve, okay, and this is what the the step function profile is trying to. So basically the step function profile is trying to mimic the behavior of this real curve, because we cannot analytically analyze the behavior of this blue curve, okay, because then there is this distribution here. So how can we apply the band emission concept for this blue curve? That's not possible, right? So what we are doing is, in order to fit the analytical framework that we develop, we are actually kind of mimicking the behavior of the real curve as this red curve, as you have seen. That's the first thing. The second thing is that what they're asking you is to calculate this total hemispherical emissivity. So we will start off by what they're actually seeking us to calculate. So they're asking us to calculate this epsilon, which is nothing but the total you know hemispherical emissivity. And from its very definition, you can say that this total hemispherical emissivity, as we just now saw, this is nothing but the ratio of the total emissive power, or the total hemispherical emissive power of a real surface to the emissive power of a black body. Okay, that comes from its definition basically. But what we are given is the spectral dependence and not directly the total dependence. And the total dependence is in fact what we are actually trying to calculate. So what we will do is we will write this as an integral from 0 to infinity, as we just now saw. This is E lambda as now a function of lambda and temperature, and this is d lambda by integral 0 to infinity EB lambda. Okay. Okay, we don't in fact require to calculate this EBT, I mean to write this EBT in this form. The reason behind is that I can still use the Stephen-Boltzmann law to basically write this. Okay, so what we are just doing is, because we know that because we know that there is a spectral dependence, what we are doing is we are writing the total emissivity of a real surface as this form, which is integral 0 to infinity E lambda times D lambda basically. Okay, but we know that, sorry, so I don't know why, sorry guys, I don't know why this, okay, anyway, so we know that from the definition of spectral emissivity, which is equal to the emissive the spectral emissive power of a real body to the spectral emissive power of a black body. Okay, we can then write that this E lambda, which is the spectral emissivity, which we have written over here, this is equal to the spectral emissivity epsilon lambda divided by this EB lambda. That's all that you write. That comes from the definition of the spectral emissivity that we just now saw. So if we substitute this over here, we can write that the total hemispherical emissivity is actually integral over 0 to infinity. Okay, the spectral emissivity times the spectral emissive power of a black body, okay, integrated over all wavelength d lambda divided by sigma times TB raised to the power 4. Okay. I hope you can understand this. So, so what we are just doing is we are first writing the very definition of total emissivity as the emissive power, of the real body to the emissive power of a black body. Then I have said that the emissive power of a real body can be written as the spectral emissive power integrated for the or integrated for the entire band of wavelength. But we know that this EBT is just equal to sigma times t raised to the power 4. And then what we are doing is we are kind of replacing this spectral emissive power of a real surface in terms of a black surface by introducing the spectral emissivity here. So then this equivalently just becomes equal to integrated over all wavelength, the spectral emissivity times the spectral emissive power of a black body divided by sigma times t raised to the power 4. Okay. Now, the thing is, you cannot bring this epsilon lambda outside the integral here and just utilize the band emission function as of now, because this epsilon lambda is essentially a function of wavelength. Okay. So what we'll do is, in order to so we'll use the fact that, so we will try to see within which band is this spectral emissivity constant. For instance, you can interpret that within the band 0 to 2 micrometer, okay, epsilon lambda is just equal to epsilon 1. So what we will do is we'll utilize this information and then write this as follows. So what we'll do is we'll write epsilon as integral 0 to lambda 1, okay, epsilon lambda 1, because we know that within this band your epsilon lambda is equal to epsilon lambda 1 times EB lambda d lambda plus the next band is from lambda 1 to lambda 2. So this becomes lambda 1 to lambda 2 epsilon within the band lambda 1 to lambda 2 times EB lambda d lambda, and then it is 0 because we know that epsilon is 0 from 5 onwards basically. Okay, so then we can write this as sigma times TB raised to the power 4. Okay, and I hope you understood. So what we are doing is we are basically breaking this in terms of the bands where the spectral emissivity is constant. The reason why we are doing this will be very much clear, will be clear from now. Okay, so we are writing this 0 because we know that greater than 5 micrometer our E lambda is basically 0, the spectral emissivity is 0. Okay, so then I can write this epsilon as integral 0 to lambda 1 epsilon lambda 1 EB lambda d lambda by sigma TB raised to the power 4 plus integral lambda 1 to lambda 2 epsilon lambda 1 to lambda 2 EB lambda d lambda by sigma times of TB raised to the power 4. Now, the good thing is within 0 to lambda 1, as you can see from your figure, within 0 to 2 micrometer, okay, your emissivity is just constant. So this means this epsilon 1 will now come outside the integral, and that is one of the most important concept of this exercise. Trying to identify within which band your spectral emissivity is constant. Okay, and then I can write this epsilon as epsilon lambda 1, because within 0 to lambda 1 I know that the band is, I mean the emissivity is just constant, and that is equal to 0.2. Okay, so then this can be written as integral 0 to lambda 1 EB lambda d lambda by sigma times of TB raised to the power 4 plus this will become epsilon lambda 1 to lambda 2, this integral lambda 1 to lambda 2 EB lambda d lambda by sigma TB raised to the power 4. Okay, because we know that within the band within the band lambda 1 to lambda 2, this emissivity is also constant, and that's the reason why it will also come outside the integral. That is, within bands the spectral emissivity is since it is written as a step function, it is constant within band 0 to lambda 1 and within band 0 to lambda 2, sorry, lambda 1 to lambda 2. Okay, I hope you can understand this. So I hope you can understand this step from this step, and this is I would say this is the most crucial step in this exercise here. Now you so what basically is this? So what does it say? It says that, so first of all, this looks like a fraction, and it says that out of the total, out of the total emissive power, what is the emissive power that is lying between the band 0 to lambda 1? So this isn't it just equal to the band emission function f 0 to lambda 1? This is just the band emission function, right? And similarly, this thing, from the definition of the band emission function, this just becomes f lambda 1 to lambda 2. Okay, so I can equivalently write the total hemispherical emissivity as the spectral emissivity for the wavelength lambda 1 times f 0 to lambda 1 plus epsilon lambda 1 to lambda 2 times f lambda 1 to lambda 2. But we know that these functions can only be evaluated if I have the range from 0 to some generic lambda I, which means I can write, I now also need to write the fact that this f lambda 1 to lambda 2, this can be written as f 0 to lambda 2 minus f 0 to lambda 1. This is something that we just derived this when we have studied the band emission function just 1 hour ago. Okay, so we will then utilize this over here, and then we can write this epsilon, which is the total hemispherical emissivity, as epsilon 1 times f 0 to lambda 1 plus epsilon lambda 1 to lambda 2 times f 0 to lambda 2 minus f 0 to lambda 1. That's it, guys. That's all that you need to do. So this is what the expression of the total hemispherical emissivity would look like in terms of the spectral emissivities. So that's it. So you know what is epsilon lambda 1. We know that the epsilon lambda 1 is equal to 0.4 and epsilon lambda 2 is equal to 0.8. Okay, and so then we can write this. So this is just equal to 0.4. This is just equal to 0.8, and since you know that your your lambda 1 is equal to, so what is your lambda 1? Your lambda 1 is equal to 2 micrometer. So what you can do is you can calculate lambda 1 times temperature, which just comes out to be 2 micrometer multiplied by 1600, which comes out to be equal to 3200 micrometer. So corresponding, so now you need to understand that corresponding to this lambda 1 times T, which comes out to be equal to 3200 micrometer, you basically have this f 0 to lambda 1 from the table that I just now saw. that I just took it from the book of infrared. This just comes out to be equal to 0.138. That's it. So, and then if you calculate lambda 2 times T, this basically comes out to be equal to 8,000 micrometer Kelvin, and corresponding with this, the band emission fraction is uh, equal to 0.856. That's it. You just now need to substitute values. So your total emissivity is equal to 0.4 times this f0 to lambda 1, which is 0.318. I believe you know how this basically came, right? Because it's just the table. For instance, if I have, so if you remember the table that we saw, if I have a multiplication of this, okay, if I have a multiplication of this, you can basically get what is the f0 to lambda. That's all that we are doing. We are just looking this table 2.2 in the book of infrared. That's all. Okay, so then this epsilon is 0.4 times 0.318, plus then the next epsilon 1 to 2 is 0.8, so this is 0.8 times f0 to lambda 2 minus f0 to lambda 1, so this becomes 0.586 minus 0.318, and if you just do this simple math, you can get your total hemispherical emissivity as 0.558. That's it, guys. That's your, so this is your total emissivity, or sometimes it is also known as the total hemispherical emissivity. Okay, that's the first part, and I hope you have understood whatever we did here, and basically this important step of defining the band emission functions within the intervals, and then identifying the band within which the spectral emissivity is constant. Okay, that's one of the key aspects of this exercise that we just now performed. All right, the second thing that we need to evaluate is to evaluate the emissive power, and that is now very easy because the total hemispherical emissive power or the total emissive power can be now written as the total emissivity, which is equal to epsilon this times sigma times TB raised to the power 4, and then you can define the total hemispherical emissive power as the total emissivity times sigma TB raised to the power 4, the total emissivity being 0.558, sigma is 5.67 into 10 to the power minus 4, and then your temperature, if you remember, it was 1600 to the power 4, and then this just come out to be equal to, so if you calculate this, it will just come out to be equal to 207 kilowatt per meter square. That's your, so that's the total emissive power of the real body, basically. That's it. That's it, guys. Okay, I hope you have understood whatever we did in this exercise. I'll stop here for a couple of minutes just for you to, digest whatever we have did, and I believe this is a very important exercise because it clarifies your concept of the band emission functions. It clarifies your concept of of how to deal with real bodies by introducing this emissivity, and then also trying to understand how do you define the spectral emissivity. Because if you remember, we started off from the very definition of total emissivity and then wrote the emissive power, the total emissive power of the real body, as integral 0 to infinity the spectral emissive power divided by the emissive power of the black body, which is sigma times T raised to the power 4. That's an important step that we did. And then what we did is, in order to bring in the spectral emissivities, we wrote that from the definition, we wrote that the spectral emissivity is equal to the spectral emissive power divided by the spectral emissive power of a black body. And then we wrote this spectral emissive power of the real body as the function of the spectral emissivity times the spectral emissive power of a black body. And then we wrote this integrals from 0 to infinity as the integrals written in these bands, and we know that after 5 micrometer this is equal to 0, so we just kept the integrals from 0 to lambda 1 and from lambda 1 to lambda 2. And then we utilize the fact that within lambda 0 to lambda 1, my spectral emissivity is constant, and that's why it came out of the integral, which then reduces the fraction to these band emission functions that we can evaluate. And since we knew the wavelength and the corresponding temperature, we can very nicely calculate the band emission function. For instance, if we knew what is lambda 1 and if you know what is temperature, you can basically calculate this because you know that your temperature is just 1600. So that's what basically we use to calculate this band emission function. Just substituted it in order to calculate the total emissivity here. Okay, and then after calculating the total emissivity of the real surface, we calculate the total emissive power of the real surface by just multiplying with the emissive power of the black body, which is just sigma times TB raised to the power 4. Okay, I believe this is clear up to this point. So I'll end this class by trying to understand two more things. As I said, so there is something which is known as the Kirchhoff's law. So although I'll not prove it, I will state that as per the Kirchhoff's law, you can say that your spectral, directional emissivity, which is denoted at epsilon lambda comma theta, which is of course a function of lambda, theta, phi, and temperature. This is equal to the spectral absorptivity, directional absorptivity, which is epsilon, which is alpha times lambda of theta, which is of course a function of this lambda, theta, phi, and t. So the Kirchhoff's law just says, so according to the Kirchhoff's law, it says that the spectral directional emissivity is equal to the spectral directional absorptivity. That's what precisely the Kirchhoff's law says. And remember, this is applicable, this law is applicable, this is always applicable because my epsilon lambda theta and alpha lambda theta are inherent surface properties. Meaning, so since I have written it for a particular wavelength and for a particular direction, this emissivity, the spectral directional emissivity and the spectral directional absorptivity, this is just the surface property because I have written it for a particular wavelength and at a particular direction. Okay, and of course at a particular temperature. So that's why this is just a surface property, and that's the reason why you can use this and that's the reason why this Kirchhoff law is always applicable. Okay, and according to this law, as I said, the spectral directional emissivity is equal to the spectral directional absorptivity. But this law doesn't say that epsilon lambda is equal to alpha lambda. This is not applicable because this says that now I have applied this for in the case where I have just neglected the direction. But for diffuse body, you can say that epsilon lambda is equal to alpha lambda because you know that for diffuse body the properties are independent of direction. So so the corollary, I can say that for a diffuse body, although this is not in general true, for a diffuse body, the Kirchhoff's law simplifies to epsilon lambda, which is just a function of lambda and t, and the absorptivity, which is also just a function of lambda and t. So this is true. So this particular thing is true for a diffuse body. So please pay attention here that this is not always in general true, but for a diffuse body, since I know that the properties are independent of direction, I can write that epsilon lambda equal to alpha lambda. Now, there is also something which is known as a gray body, and for a gray body, it means that the radiation properties are independent of wavelength as well, which means that if I have a diffuse and a gray body, then I can write that this epsilon basically, which is now just a function of temperature, is equal to alpha, which is just a function of temperature. So the Kirchhoff's law simplifies to the fact that the total emissivity is equal to the total absorptivity only in the case when I have a diffuse and a gray body, and this is very important. Okay, so this is true. So this is true for a diffuse plus a gray body. But remember, these definitions that epsilon equal to alpha and epsilon lambda equal to alpha, these are for generic cases. For instance, epsilon lambda is equal to alpha lambda, that is the spectral emissivity is equal to the spectral absorptivity for a diffuse body, and epsilon is equal to alpha is only true, that is the total emissivity is equal to the total absorptivity. This definition is only true if you have a diffuse and a gray body. And then we also saw the definition of gray body, which says that the radiation properties are independent of wavelength. But the most general form of Kirchhoff's law is this, which says that the spectral directional emissivity is equal to the spectral directional absorptivity. Okay, this is the most general form of Kirchhoff's law. I understand we have not proved this. You can basically prove this, but I believe we have already witnessed this proof in. So this proof is there in the book of Incrofra. Also, I believe you saw this in the lecture classes in this for this week. Okay. So I hope you have understood the most general form of Kirchhoff's law and under what circumstances you can write the Kirchhoff law in this form and in this form basically. Okay. So this precisely, ends your discussion on real surfaces. And in the next class, we will look into something which is known as radiation. So in the next class, we'll look into something which is known as the radiation view factors, and that is one of the most important aspects in radiation heat transfer, because it quantifies how much radiation is being uh, emitted by surface 1, that falls on, or that is intercepted by surface 2, and that is precisely defined by view factor. And we'll look into certain general properties of view factor. For instance, there is something which is known as view factor reciprocity relation and summation rule and things like that. We'll look into that. But at least from up to this point, you must be, at least from the discussions that we had in the past 2 weeks, you must be, comfortable enough to identify the various radiation fluxes that we saw, the definition of the intensity of radiation, the spectral and the directional aspect that comes into it, and then, the aspects of a black body, the general properties of black body, the Stephen-Boltzmann law, and also there is something which is known as the Wiens displacement law. So the Wiens displacement law, although I have so the Wiens displacement law is already discussed in the lecture classes. That's why I have just not repeated it for the sake of repetition. But it is just says that lambda max times the temperature is equal to a constant. This constant, I believe, is 2897.6 micrometer Kelvin, I guess. So the Wiens displacement law just says that lambda max times T is just a constant basically. And this comes, if you draw the graph between EB lambda and lambda, you will basically get the Wiens displacement law if you connect the peaks of those graph for different temperatures that you draw. Okay, that's the idea. I have not, discussed that because this has already been discussed in the lecture classes, but that's from where you get the Wiens displacement law. Okay, which says that the wavelength corresponding, the maximum wavelength in the graph of this EB lambda and lambda times temperature is always equal to a constant basically. Okay, that's what the Wiens displacement law says. We already saw the Stephen-Boltzmann law, and there is also something which is known as the Planck's law. We can also that had already been discussed. So these are the three aspects that we consider, that we generally discuss for black bodies. And then what we saw something today is known as the band emission function, where we seek to understand what is the emission that lies within a certain band out of the total emission that basically goes from 0 to infinity, and that is defined by that fraction f0 to lambda. And we saw that if we know a particular wavelength, and if we know a particular temperature, we can actually calculate this f0 to lambda from the table that we just saw in the book of Incorporate, that if you multiply lambda times t, corresponding to that, you know the fraction f0 to lambda. Okay? And that's how we calculate these band emission functions or fractions. Okay? And then we saw, and we went into the idea of a real body, and we first defined what is the total emissivity of a real body. From there, we defined the spectral emissivity of a real body. And after defining the spectral emissivity, we also saw what is the spectral directional emissivity written in terms of the intensity of radiation. For instance, the total emissivity is, or the total hemispherical emissivity is the emissive power of a real body to the emissive power of a black body. The spectral emissivity is the spectral emissive power of a real body to the spectral emissive power of a black body, and the spectral directional emissivity is equal to the spectral directional intensity of radiation to the spectral directional intensity of radiation of a black body. That's the that's how the hierarchy actually goes on, and that's how we have defined. And then we have utilized all this concept in the solving a numerical, where we saw that the spectral emissive power was a function of wavelength, and our idea was to calculate what was the total emissive power. And then there we have utilized the concept of band emission by decomposing the entire, you know, uh, integral from 0 to infinity into the steps, into the bands where, the spectral emissivity was constant, and that led to, the epsilon lambda coming out of the integral, and we basically calculate what is the total emissivity out of there. And then from the total emissivity we calculated the total emissive power by using the Stefan-Boltzmann law, where we use the fact that the emissive power of a black body is just sigma times the temperature of the black body raised to the power 4. Okay, that's what we define. So the beauty of the Stefan-Boltzmann law is that even if you know the temperature of the body, you can calculate, if you know the emissivity, you can calculate the emissivity of the real surface, even if you know that had that real surface been a black body of that at that same particular temperature, basically. So actually the emissivity is defined as the emissive power of a real surface to the emissive power of a black body at that particular temperature. That aspect is important. Okay, and that's how we basically can calculate the emissivity, or the emissive power of a real surface. And after that we have defined something today, which is known as the Kirchhoff's law, which the most general definition without any assumption is that the spectral directional emissivity is equal to the spectral directional absorptivity. And then we saw that for a diffuse body, where the properties are not dependent on direction, we can say that the spectral properties are equal, which is the spectral emissivity is equal to the spectral absorptivity. And then for a gray and a diffuse body, we saw that the total hemispherical emissivity is equal to the total hemispherical absorptivity. But remember, this is only true if you have a diffuse and a gray body, and this is true if you just have a diffuse body. But this is the most general form of the Kirchhoff law, because it specifies, because it is just applicable for an inherent surface only, because it is independent of wavelength, and it is also independent, I mean, you are looking at a particular wavelength and at a particular direction. Okay, all right, so this is something that we did. So we had a nice little extensive discussion on the various aspects that we discussed just now. And so we'll not introduce any new further topic now. If you have any doubts, you can always use the discussion forum of this course to basically, clarify your doubts. And we will meet again in the next week using the same link and at the same time, from 3 to 5. And as I say again, if you have any questions associated with these discussions that we had, or the numericals that we solved, or the assignments, please feel free to use the discussion forum of the course. And yes, we'll meet again using the same link at the same time. Thank you very much. So basically I think we'll have couple of classes. Maybe we'll have 2 to 3 more interactive sessions for this course, and I think we'll have 3 more interactive sessions where we'll be discussing something which is known as this view vectors. And then there is something which is known as radiation seals, and things like that. And then we will just end up the discussion on radiation, and then at the last class we'll do a final recapitulation of all the heat transfer aspects that we discussed, and then we'll end it. We'll end the session, and after that you basically have your exams for this course. That's the idea. Okay, so all right guys, we'll end up today. We'll meet next week at the same time, as I said, using the same link. Thank you very much guys for attending the session. We will meet again next week, in the next week. Thank you guys.